Hello and welcome to our project where we're going to be doing a side channel attack on a field programmable gate array. My name is Brandon Poorman. I'm accompanied by my partner Javier Gutierrez. And this is for EC 150 Cybersecurity Fall 2021. So the general idea of our project is we're going to be using an on-chip design on a field programmable gate array FPGA to perform a side channel attack and spy on a multi-tenant FPGA user. And what a multi-tenant FPGA is FPGAs are low cost and programmable, and they have applications in cloud data centers now, where users can share resources on the FPGA to perform a number of different tasks like machine learning or network cryptography. And the vulnerability in this is that multiple users can program and place and route their own designs on the hardware, where a malicious user could place and route a malicious design near a victim and try to spy on that logic and potentially gain access. To give a little bit of background is we're going to be implementing an AES module on the victim logic, which is completely separate from the malicious user logic. And we're going to be using a ring oscillator, aka RO, which we use as a receiver on the crosstalk of the wire near the AES module. So we're going to be placing and routing 16 ring oscillators around an AES module, which are not physically connected in hardware or software. The ring oscillator is just near the AES module. We're going to use that ring oscillator to perform a side channel attack and attempt to gain information on that AES module.
So this is an overview of the chip planner under Quartus, the program Quartus. So this is essentially the view of the chip that is being shared amongst users, say on the cloud. So this is on our board that we implemented. We implemented the 16 ring oscillators and the AES module. So those blue squares, those are the 16 ring oscillators and surrounding the AES module. So it's kind of attacking it and being near it, and that's where we can gather data that's going to be used to infer. This is just showing the encryption that the AES was able to do. So it takes the 32-bit value and it with the key encrypts it and it decrypts it.
So we set up a TCL script on the right here that essentially takes and writes to the ring oscillators to enable the enable signal, set it to 1 to begin the oscillation and find the frequency of the nearby AES models. So without AES running, we have no values because the AES has no power and is not being ran. And then this is what happens when we do have the AES module running. We have a number of different oscillators and we check this multiple times. So what you're looking at is the oscillation frequency of each of the ROs next to the AES models. So we can use this information to perform a number of different aspects. We don't specifically find the AES key based off of this, but what we're looking at is the first step in order to find the AES key. In terms of defending against this attack, there's a few different countermeasures. The main countermeasure is to actually use the ring oscillators or multiple ring oscillators spread out throughout the chip to detect any anomalies in the hardware. Instead of using the ring oscillators to attack, we can use them to defend. Because each chip is unique and every ring oscillator will oscillate at a different fundamental frequency inside the chip, if there is a change on the chip or there's some kind of malicious logic, we can detect that with a ring oscillator. Now, one trade-off is it increases the power consumption, but overall ring oscillators are not too heavy on power consumption. And then another countermeasure, which is not able to be implemented, is to restrict placement and routing of modules near sensitive hardware blocks on the chip. And this would be done on the cloud provider side. Now, the trade-offs would be increased demand on monitoring and lack of user flexibility in design. This concludes our presentation on side channel attacks on FPGAs.